You know that feeling when a music app claims to shuffle your playlist, but it just kind of keeps playing the exact same three artists over and over? Well, that's fake randomness. Today, in this explainer, we're going to shatter the illusion that picking at random is actually random. We are joining our main character, Dr. Mira, on a high-stakes comic case investigation to eliminate selection bias from her research and achieve true mathematical randomness. If you're a PhD scholar, an MBA student, or part of a corporate research team, you already know that bias is the absolute enemy of valid data. So let's follow Dr. Mira. She locks down the rigorous neutrality required for a genuinely random sample. Now, this quote right here sets the absolute baseline for Dr. Mira's entire investigation. Just because a researcher closes their eyes and points blindly at a list absolutely doesn't mean the result is random. True randomization is a rigorous, mathematically neutral procedure. It requires that every single element in the population has a known, non-zero, and completely equal probability of being selected. Let's see exactly how Dr. Mira builds this neutral process from the ground up. All right, let's open the case file with Chapter 1, the Sampling Frame Challenge. So our case begins with Dr. Mira staring at a massive, disorganized data set. She quickly realizes you can't just randomize in a vacuum. You can't draw from some vague concept of a target population. You need a sampling frame. Whether that's a physical employee payroll, a university student registry, or a customer database, it literally has to be a tangible, complete representation of all elements before you select a single person. Think about the infamous 1936 Literary Digest poll. They incorrectly predicted the U.S. presidential election simply because their sampling frame relied on phone directories and club rosters. They completely excluded working-class voters who didn't own phones. If your starting list is fundamentally flawed like that, your entire operation is compromised on day one. But, a raw list is never ready for action. Before a single person gets selected, Dr. Mira has to execute this tactical data cleaning protocol. She scrubs the file to remove duplicate entries, clears out ineligible cases, checks for missing contact details, and rigorously applies her inclusion and exclusion criteria. Think about it. If she leaves in duplicates, boom, those people suddenly have double the chance of being selected. That completely destroys the neutrality of the draw. As any seasoned researcher knows, the glamour of analysis is built entirely on the grueling sweat of data cleaning. Which brings us to Chapter 2, the one-chance rule. With the data beautifully cleaned, Dr. Mira arms her dataset to establish total equality. She assigns a unique ID to every single eligible case, say from 001 all the way to 2000. Why is this absolutely crucial? Because every single participant needs exactly one clear, quantifiable chance of selection. By giving everyone a unique code, she ensures the selection process targets neutral numbers rather than human names, wiping subconscious bias out of the equation entirely. Okay, moving on to Chapter 3, Methodological Tactics. Now that her targets are locked with unique IDs, Dr. Mira has to choose her weapon for extracting the sample neutrally. To avoid that pesky human bias, she has to completely surrender her control to one of these neutral tools. She can fire up a computer-based random number generator, use the Excel rand function, or if she's dealing with a really small list, just go with the classic lottery method, literally drawing numbers blind from a hat. The specific tool doesn't actually matter as much as the fact that it removes her personal choice from the selection. Let's look at her first tactical option, simple random sampling. Here, Dr. Mira just uses her generator to pick IDs, ensuring each eligible person has an equal, mathematically sound chance of being chosen. She reads off the generated random numbers and just matches them to her unique IDs until her required sample size is hit. It's highly accurate, very robust, but remember, it strictly requires that perfectly clean sampling frame we talked about earlier. Alternatively, for massive corporate or academic datasets, she might deploy systematic random sampling. First, she calculates a sampling interval. So, say you divide a huge population of 2,500 by a target sample size of 100, that gives you an interval of 25. She rolls a random starting point between 1 and 25, and then efficiently pulls every 25th case from her dossier. It's an incredibly smart tactic for saving time while maintaining integrity. But wait, hit the brakes for a second. We have a massive warning alert that halts the investigation. Dr. Mira has to ask, what if the list itself is hiding a pattern? Systematic sampling is brilliant, but it is highly vulnerable to periodicity. These are underlying repeating cycles hidden right inside your data frame. Let me give you an example. Imagine her sampling frame is a joint bank account list arranged alphabetically by household, which inherently alternates between male and female account holders. If Dr. Mira uses an even-numbered systematic interval on this cyclical list, she might accidentally select only male accounts. No way around it. That completely compromises the sample. She absolutely must inspect the list for hidden patterns before ever deploying this method. Let's flip to Chapter 4, Visualizing Subgroups. So, what happens when her population involves specific, distinct minority groups that could easily just get left out by pure mathematical chance? Enter the stratified sampling dashboard. Using stratified random sampling, she divides her population into mutually exclusive strata first, like dividing employees by job roles, sector, or gender. Then she randomizes within those specific groups. This guarantees that her final sample actually reflects the true proportions of the overall population. Sure, it takes a bit more work up front, but the precision is completely unmatched. On the flip side, what if she doesn't even have a full master list of every single individual? She switches to cluster sampling. Instead of individuals, she randomly selects entire organizational units, like specific schools, firms, or regional districts first. Once those clusters are selected, she then samples the participants inside those specific sites. It's a super practical workaround when a massive, unified sampling frame is just impossible to get your hands on. Okay, Chapter 5, Crisis Management and Non-Responses. Because let's be real, even the perfect plan hits a snag in the real world. What happens when a randomly selected participant simply refuses to participate, drops out, or can't be reached? This right here is where the true integrity of the whole study is tested. We have to ask the tough questions. Did the researcher just casually replace the non-respondent with someone sitting nearby? Did they literally regenerate the random number until a better or easier name appeared? These casual replacements are massive red flags. These are the exact common errors Dr. Mira must avoid at all costs. Hand-picking substitutes, ignoring duplicates, or making casual replacements are absolutely fatal to a study's validity. If she wants her findings to survive intense academic peer review or a tough corporate board meeting, she cannot let human convenience override mathematical neutrality. Bias will always creep in the exact second you drop your guard. So the strict rule here is the replacement rule. Dr. Mira knows she has to adhere to a predefined replacement methodology, like randomly selecting a backup from the exact same stratum, or simply document the refusal and report the non-response rate clearly. She must never, ever just grab the next convenient person on the list, period. And finally, we reach Chapter 6, the final dossier. Dr. Mira has navigated this sampling frame, chosen her tactical methods, and handled the crises without compromising her data. Now she compiles this audit trail. This is her ultimate shield. It is a meticulous, step-by-step record of everything: the source of the sampling frame, the exact date it was pulled, the total eligible cases, the specific randomization tool used, the computer's seed value, the selected IDs, and the rules for replacement. By logging all of this, she makes the entire operation undeniably transparent. Before she officially closes the case file, she runs through this final checklist. Is the frame clear? Are all eligible cases included? Was the selection method truly neutral? Are the non-response rules documented? And here is the absolute most important question for all our scholars and executives out there. Is the full sampling process reproducible? If another researcher picked up this exact dossier, could they reproduce the exact same neutral process? If the answer is yes, the mission is a massive success. And that brings us to the end of our investigation. Ultimately, what you should take away from this explainer is that true randomization is not some happy accident. It is a meticulously engineered, unyielding procedure. Bias is always just waiting to creep in through sloppy data or convenient little shortcuts. So I leave you with this question to ponder for your own professional work. Is your next sampling process going to be truly random or just an illusion? Thanks for joining Dr. Mira and me today.